Hello everyone, in this lesson we're going to be covering chain rule to find derivatives. This lesson does also include implicit differentiation, but I'm actually going to record that as its own video so we can really kind of hone in and focus on that. So our chain rule says that if we have g of x, which is differentiable at x, and fu, which is differentiable at g of x, then f, which capital F, is equal to f of g of x is equal to f of g of x is differentiable at f. That is to say that if we take the derivative f prime, this is going to be equal to f prime of g of x times the derivative of g of x. So what this means is that if we have dy dx, we can actually use what's called u substitution, and this will become dy du times du dx. And I'll talk later whenever we get into implicit differentiation and stuff like that, why this is true. Now, most people just generally think of the fact that if you were to cancel this du and this du, then it'd be dy dx. This works, but it's not actually true. And again, I'll explain later on why that is. But what we're going to be doing is we're going to be using something called u substitution, where we're going to take whatever this inside term is, and we're just going to replace this with a u. So this would pretty much be f prime of u times, of course, the derivative of g of x. Now, for longer chains, we have if ht is differentiable at t, and g of x is differentiable at ht, and fu is differentiable at g of x, then we would have f of g of h of t. If we take the derivative of that, this is going to be, so if we have f of g of h of t, and we take the derivative of this entire thing, this is the same thing as we are going to take the derivative of the outer term, f of x. So this would be our fu, right? So this would be g of h of t times. Then we take the derivative of the middle term. So this would be g prime of h of t times, and then we take the derivative of our most inside point, so h prime of t. So you could also think of this as, suppose that this g of h of t is u, and h of t is going to be v. This would be the same thing as saying f prime of u times g prime of v times h prime of, in this case, t. So what we're really doing here is we're saying that dy dx is equal to dy du times du dv times dv, in this case, sorry, this shouldn't have been dx, this should have been dt, dt. And again, like I said, you can't just cancel them, but in essence, it does work. So of course, du's, dv's, and this would leave us with dy dt. Again, I'll talk later on about why that's not actually the operation that you're doing, but in the end, it does kind of work when you're just trying to think about how do you figure out what is your actual derivative that you're taking. Our actual derivative is dy over dt. Now, before we do a bunch of examples about using the chain rule, I first want to talk about taking exponential functions. So if you remember, the derivative d dx of e to the x is just going to be equal to e to the x. And this is going to be using our chain rule. We can actually derive what f of x equals some constant b to the x is when we take the derivative when b is not equal to e. So first we're going to do is we're going to start with b to the x. And in order to do this, we're then going to take the exponential of this, but anytime, just like with a square and a square root, the thing that cancels out an exponential is the natural log. So we're going to change this to e to the natural log of b to the x, which, if you remember your rules from natural logs, you can actually take a power and you can pull it out of your natural log. So this would end up being e to the natural log of b times x, where b is just some constant. So therefore, when we take our derivative of this, d dx of b to the x, this is going to be the same thing as taking the derivative d dx of e to the natural log of b times x. Well, when we take the derivative of e to some power, this is just going to be e to that some power, natural log of b, times. Now we're going to take the derivative of the inside, right? Because that's our chain rule in this case, is that it's the outer term, e to the u, and then times the derivative of whatever that inside term is. So when you take the derivative of natural log, d dx, natural log, I'm just going to say of some, I'll say this is u. When I take the derivative of this, this is going to end up being, let's do it u prime, so d du. This is going to end up being 1 over u, and then you're going to take the derivative of whatever was inside of that natural log, right? So that'd be your d dx in this case. So what we're going to do is we're going to take the natural log of this b, right? So remember, this is a b, not a 6. So this is going to end up being 1 over b. So then I'm taking the derivative d dx natural log of b times x. So if you remember, this is actually going to use our product rule. So it's going to be the derivative of the natural log of b, which is just going to be 1 over b. X is just going to be x. And then plus, take the derivative of x, going to be 1. This is going to be natural log of b. So what we're going to end up being left with is e to the natural log of b times x times the natural log of b. Right, I just made it a capital B again, so we didn't confuse it with a 6. Well, guess what? E to the natural log, this is again just going to cancel, right? So I'm going to bring this x back up to the top, so this will be b to the x. So this is just going to be equal to b to the x times the natural log of b. So whenever you have some constant to some exponential, in this case x, it is just going to be that term, b to the x, times the natural log of whatever your base is. Okay, and we're going to have an example later on where we're going to do this as part of our chain rule examples. For our first example, we have the function f of x is equal to the square root of x squared plus 1. And we want to figure out what is the derivative. So before we do that, as always, first thing I'm going to do, I'm going to rewrite this. So this is going to be x squared plus 1 to the 1/2 power. This is going to be our u. So when we take the derivative, f prime of x, this is going to be f prime of u times, and then the derivative of u, whatever that inside term is. So I'll just call it u prime. Okay, so first things first, let's take the derivative of the outsides. This is going to be 1/2, leave the inside alone, x squared plus 1, and then this is just going to be power rule, right? Think about this. This is u to the 1/2. So this would be 1/2 u to the, and then you subtract 1 from it, you get negative 1/2. So this becomes 1/2 x squared plus 1 to the negative 1/2 times. Now we take the derivative of the inside. We have x squared plus 1. So that's the derivative of x squared plus the derivative of 1. Derivative of x squared is just going to be equal to 2x plus 1. Derivative of a constant is equal to 0. So we're going to get 1/2 x squared plus 1 to the negative 1/2 times 2x. So if I bring my 2x over here, I get 2x over 2. That's just going to leave me with x. And then if I look at this term here, x squared plus 1 to the negative 1/2, the negative is just going to bring it to the denominator. This would be over x squared plus 1 to the 1/2. Or if I want to put it back in terms of my original function, which was a square root, this is going to be equal to x divided by the square root of x squared plus 1. For my next example, I actually have two different functions that I want to take the derivative of and kind of just compare them. So the first one we have is y is equal to sine of x squared. And the second one is y equals sine square of x. So if we were to take the derivative of this first one, in this case, my fu in this is going to be sine of u. And my g of x is going to be this middle term, x squared, right? So it's chain rule. Take the derivative of the outside as sine of u times the derivative of the inside term, which is g of x. So my y prime is going to be f prime of g of x times g prime of x. So pretty much what this means is take the derivative of sine. What are we going to get? Well, this is going to be equal to cosine of u times. Now we take the derivative of g of x, x squared. So this is going to be times 2x. We take our u, which in this case is just going to be x squared, and we plug it back in. We get this equal to cosine of x squared times 2x. Or if I wanted to write it in terms of having 2x front, it would be 2x times cosine of x squared. Looking at our second function, what we have is y equals sine square of x. So in this case, our f of u is just going to be u squared, right? Because if you think about whenever we take the derivative of sine, so d dx of sine square of x, what you can actually think of this as is this is going to be d dx sine of x squared. So in this case, this is going to be our u. So it's going to be u squared. And our g of x is going to be sine of x. So now, whenever we take our derivative, this is going to be equal to f of g of x, so f prime of g of x times g prime of x. So first thing first, we take the derivative of, and by the way, you can think of this as, again, your u. So we take the derivative of u squared. This is going to give us 2u to the first power times, now we take the derivative of our g of x. G of x is sine of x, which means it is going to be equal to cosine of x. And then I just, by the way, this is a 1, not a prime. And then I just plug my u back in. My u was equal to sine of x. So this is going to be equal to 2 sine of x times cosine of x. So you can see here that by having the x squared inside, we actually don't take that square derivative until the inside part of the chain. Versus when it's sine square x, we actually take that as our outside of the chain, and we end up getting a very different answer. We have cosine x squared times 2x versus 2 sine x times cosine x. What about if we want to differentiate y equals x cubed minus 1 to the 100th power? Well, in this case, right, if we have y equals f of g of x, our f of x, or fu, if you will, so fu is going to be equal to u to the 100th power. And then our g of x, our inside term, is going to be equal to x cubed minus 1. So when we take this derivative, what we're going to do is I'm just going to actually jump straight into solving it the way that you all will actually probably solve it, which is take the derivative of the outside, so bring the 100 down, leave the inside alone, x cubed minus 1. So 100 minus 1 is going to be to the 99th power, and then times the derivative of the inside. X cubed minus 1 is going to give me 3x squared. So then, of course, if I bring this 3x squared up front, this is going to end up being 300x squared x cubed minus 1 to the 99th power. What about if I have f of x is equal to 1 over the cube root of x squared plus x plus 1. Now, what you could do, you could solve this using your quotient rule, right? Treating this as f, treating this as g, but that would be a lot of extra steps. So instead, what I'm going to do is I'm going to rewrite this as x squared plus x plus 1. Now, again, we have a cube root, which means that this is to the 1/3 power. And it's in the denominator, and I want to bring it to the numerator, so I'm going to take a negative power. So now, if I were to treat this as my u, right, so I have u to the negative 1/3, when I take the derivative of that, I would get, so I'm going to rewrite it this way. I'm going to write it as d du u to the negative 1/3 times d dx, right? So I'm taking the derivative with respect to x of the inside now. X squared plus x plus 1. So doing this, when I take the derivative of u to the negative 1/3, I bring the negative 1/3 down, so minus 1 over 3, u to the 1/3 minus 1 is equal to 1/3, minus 1/3 minus 3/3, which would give me minus 4/3, times the derivative of x squared would be 2x, plus the derivative of x equals to 1, and then plus the derivative of constant is equal to 0. So we have negative 1/3 u negative 4 to the negative 4/3 power times 2x plus 1. So I'm going to plug my u back in. Remember, my u is x squared plus x plus 1. So this is going to be equal to negative 1/3 x squared plus x plus 1 to the negative 1/3 power, negative 4/3 power, times 2x plus 1. So now I'm going to rewrite this back in terms of an actual root because I want to get it back into the original form. So we have done the derivative now. So this is going to be equal to minus, 1/3. So I know I have a 3 in the denominator. We have negative 4/3. So this means that the negative is going to bring this down here. So we have x squared plus x plus 1 to the 4/3 power, meaning that this is going to be to the 4th power, and then the 1/3 power means that it is going to be a third root. So this is going to be 3 times the third root. Let me clean that up. This is going to be 3 times the third root of x squared plus x plus 1 to the 4th power. And then this is on the top, so this is going to be 2x plus 1. So we end up having minus 2x plus 1 divided by 3 times the cube root of x squared plus x plus 1 to the 4th power. For my next example, we have g of t is equal to t minus 2 divided by 2t plus 1 to the 9th power. So in this case, g of t is going to be equal to f of h of t. So remember, these function names, f of h of t, right? We're just not using g because it's already our main function. So that equals fu is going to be equal to u to the 9th power, right? So let's leave the center alone to the 9th power, right? So that's this whole thing inside is all going to be equal to u. And then ht is going to be equal to our t minus 2 divided by 2t plus 1. So taking our derivative of g of t, actually, no, sorry. Let's do the derivative of this real quick because we're going to have to, basically what's going to happen is this. When we take the derivative of g of t, this is going to be, we're going to take the derivative of, so d du of u to the 9th times d dx of t minus 2 over 2t plus 1. And we're going to have to end up using our quotient rule for that. So if you remember, our quotient rule is gf prime minus fg prime divided by g squared. So let's figure out what that derivative is real quick. So if this is our f term and this is our g term, this means that we're going to first leave our g alone. So this is going to be 2t plus 1 times the derivative of f. So t minus 2 gives me a derivative of 1 minus, leave f alone, t minus 2 times the derivative of g. So the derivative of 2t plus 1 is going to be 2. And then this whole thing is divided by g squared. So 2t plus 1 squared. Rewriting this is going to be 2t plus 1 times 1. So that's going to be 2t plus 1. And then minus, I'm going to distribute this 2. So it's going to be minus 2t. So minus a negative, so it's going to be plus 4 divided by 2t plus 1 squared. 2t minus 2t is going to give me, that's going to go to 0. 1 plus 4 is going to give me 5 over 2t plus 1 squared. So that is going to be what our derivative is for this inside part, right? So now let's take the derivative of the outside part. So when we take the entire derivative, going back to our original derivative, we take the derivative of the outside, so we pull the 9 down, so this is going to be 9, leave the middle alone, so this is going to be t minus 2, that's my u, 2t plus 1. Now, I took a 9 down, we're doing a power rule, right? So u to the 9th, bring the 9 down, 9 minus 1 gives me a power of 8 times. Then we took the derivative of t minus 2 over 2t plus 1, which we just said is equal to 5 divided by 2t plus 1 squared. So next thing I'm going to do is I'm actually going to simplify this a little bit. Because if I ever have, for example, something like this, a over b to some power x, I can actually write this as a to the x divided by b to the x. And that's what I'm going to do here. So I'm going to bring this 5 over to the front. So we're going to get 9 times 5 is going to be 45. And then I'm going to bring this 8th power. So this is going to be t minus 2 to the 8th power divided by 2t plus 1 to the 8th power times 1 over 2t plus 1 squared. Now you'll notice I have 2t plus 1 to the 8th power times 2t plus 1 squared. What happens when you multiply, a to the some power times a to the some other power? You just add those powers together. So this is going to end up being 45 t minus 2 to the 8th power divided by 2t plus 1 to the 8 plus 2 power, or to the 10th power. And so this would be the derivative of our original function, t minus 2 divided by 2t plus 1 to the 9th power. For my next example, we have the function y equals 2x plus 1 to the 5th power times x cubed minus x plus 1 to the 4th power. Now, if you look at this, this is going to end up being our product rule, right? Because we have some function f of x times some function g of x. Now, if you remember, our product rule is that we have g f prime plus f g prime. But because each of these is to a power, right? 2x plus 1 to the 5th power, x cubed minus x plus 1 to the 4th power. When we take these derivatives, we're actually going to have to be using the chain rule. So we have a product rule with a chain rule. So let's do it. So when we take y prime, which means we're taking the derivative of y, we're first going to leave g alone. So this first term is going to be x cubed minus x plus 1 to the 4th power. Now we're going to take the derivative of f. So we take the derivative of this, right? We take the derivative of the outside. So we're going to bring the 5 down. We're going to leave the middle alone, 2x plus 1. And we're going to bring the power down by 1. So 5 minus 1 is 4. Times, now we have to take the derivative of the inside of this function. So 2x plus 1, take the derivative of that, derivative of 2x is equal to 2. And then the derivative of 1, because it's constant, is equal to 0. So we have 5 times 2x plus 1 to the 4th power times 2. Plus, now we're going to leave f alone. So this is going to be 2x plus 1 to the 5th power times. We need to take the derivative of g. So again, leave the middle alone. We're going to bring the 4 down. So this is going to be times 4 x cubed minus x plus 1. So 4 minus 1 takes it to the 3rd power times. Now we take the derivative of the inside. X cubed is going to give me a derivative of 3x squared. Minus x is going to give me a derivative of minus 1, and then derivative of a constant equal to 0. So we have x cubed minus x plus 1 to the 4th power times 5 times 2x plus 1 to the 4th power times 2, plus 2x plus 1 to the 5th power times 4 x cubed minus x plus 1 cubed times 3x squared minus 1. So the next thing I'm going to do is I'm going to combine and pull all of the constants out to the front. So in this case, I have 5 and 2. So this is going to be equal to 10 x cubed minus x plus 1 to the 4th power times 2x plus 1 to the 4th power. The next thing I'm going to do is I'm going to roll this 4 out, so plus 4. And I'm actually going to write these so that they're in the same order as this. So in this case, I have x cubed minus x plus 1 cubed, and then times 2x plus 1 to the 5th power times 3x squared minus 1. Now you might wonder, why did I do this? Well, it's because what I'm going to do now is I'm going to see if there's anything that I can pull out from both parts. So in this case, I have 10 and I have 4. Do they have anything in common? Yes, they have a 2 in common. So I'm going to pull a 2 out. Next thing, x cubed minus x plus 1. X cubed minus x plus 1. This one is to the 4th power, this one is cubed. So I can pull out x cubed minus x plus 1 cubed. Next thing, my 2x plus 1 terms. I have 2x plus 1 to the 4th power, 2x plus 1 to the 5th power. So I can pull out 2x plus 1 to the 4th power. Now, if I do this, when I pulled the 2 out, I'm left with 5 in my constant. Times. I pulled out x cubed minus x plus 1 to the 3rd power. So I have 1 left in this one. So this is going to be times x cubed minus x plus 1 to the 1 power, right? Because 1 and then times 3, that would add to the power of 4. And then that's it for this one. Now we're going to look at our second term. I had a 4, I pulled 2 out. This is going to leave me with 2 times x cubed minus x plus 1 to the 3rd power. Well, that's this entire thing, x cubed minus x plus 1 to the 3rd power. Next we have 2x plus 1 to the 4th power. I had 2x plus 1 to the 5th power. That leaves me with one of them inside still. So 2x plus 1. And then times, this one didn't have anything outside, so this is going to stay the same. 3x squared minus 1. Okay, so now, if I could redistribute this back in, right? And I would get back to this original term here. Now I'm going to actually distribute these and see if there's any cancellation inside. So for the outside, nothing changes. 2x cubed minus x plus 1 cubed, 2x plus 1 to the 4th power. So I'm going to distribute this 5. I'm going to get 5x cubed minus 5x plus 5. And then for this one, I'm first going to FOIL it out, right? So first, outer, inner, last. And then I'll just take whatever I get there and I'll multiply it by 2. So 2x times 3x squared is going to be 6x squared. So this is going to be plus 12x, x cubed, right? X plus x times x squared. Now I'm going to do my outer terms. 2x times minus 1. So minus 2x times 2 is going to be minus 4x. Now I'm going to do my inner terms. 1 times 3x squared. So 3x squared times 2 is going to be plus 6x squared. And then last, 1 times negative 1 is going to be negative 1. So times 2 is going to be minus 2. And now we're going to see, is there anything that combines or cancels or anything like that? So again, I'm going to leave my outer terms alone. So this is going to be 2x cubed minus x plus 1 cubed, 2x plus 1 to the 4th. Okay, so now let's look at our highest power. This is going to be the cube terms. 5x cubed plus 12x cubed. This is going to give me 17x cubed. Now let's look at our x squared terms. Well, it looks like I only have the 1x squared, which is going to be plus 6x squared. So that's this term. Now we're going to look for our x terms. Minus 5x minus 4x is going to give me minus 9x. And now I'm going to look at my constants. 5 minus 2 is going to be plus 3. And this would be the simplest form that I can get this into because I was able to kind of cancel out these inside terms. And there you go. So this would be the answer to 2x plus 1 to the 5th power times x cubed minus x plus 1 to the 4th power when we take the derivative. For my next example, we have y is equal to e to the sine of x. So if we were to consider that this is my y equals f of g of x, my outside term, fu, is just going to be e to the u. And my inside term, the g to the x, is going to be the sine of x. So what this means is when I take the derivative of this, I'm going to take the derivative of my fu term, so this is going to be derivative of e to the u, times the derivative of my internal term, sine x. So then if I were to do this, this is going to end up being, right, so the derivative of e to the x or e to the u is just going to be e to the u. So this is just going to leave my term, e to the sine of x times. Now I take my derivative of the inside term. So the derivative of sine of x is going to give me cosine of x. So I'm left with e to the sine of x times cosine of x. What about if I have f of x is equal to sine of cosine of tangent of x? So in this case, I'm actually going to solve it a little bit differently, but basically doing the same thing. Is I'm going to say that this is u, and this, I'll call this v. So if I look at g of x, let's do it this way. G of h of j of x, right? Because we're just doing a higher order chain. Then my g of u is going to be sine of u. My h of, in this case I used v, is going to be cosine of v, and my j of x is going to be this internal term, tangent of x. So what this pretty much means is when I'm taking the derivative of the outside, right, so it's going to be derivative of sine of something. So the first thing I'm going to do is I'm going to take my derivative d du of sine of u times. I'm going to go in one step. I'm going to take the derivative d dv of cosine of v. And then finally, I'm going to take the derivative d dx of tangent x. So when I take the derivative of sine, I'm going to get cosine of x, so cosine of u times the derivative of cosine. So the derivative of cosine is going to be negative sine. So this is going to be negative sine of v times. What about if I have the function g of x is equal to 5 to the 2 to the x to the second power? So in this case, we're going to be doing a chain rule where we have our g of x is equal to f of h of j of x. Now remember, again, these functions can be whatever letters you want them to be. We're just not using g because that's our original function. So our f u is going to be 5 to the u. Our h of, I did z on the slides, I'll keep it consistent. Last time I did v, but I'll use z, is going to be 2 to the whatever, this would be z. So 2 to the z. And then our j of x is going to be x squared. So when we take the derivative of each of these, right? So if I took the derivative of the first one, so d du of f u, remember we talked about this whenever we did our exponential rule. This is going to be 5u natural log of 5. When I take my d dz of h of z, this one is going to end up being, same idea, it's going to be 2 to the z natural log of 2. And then we are going to have the derivative d dx of x squared, which will just be 2x. So this means that when we take our derivative, g prime of x, it is going to equal to 5u natural log of 5 times 2z natural log of 2 times 2x. And then we just plug our u and our z back in. So this will be equal to 5, and we said that our u was equal to all of this. So 2 to the x to the 2, natural log of 5, times 2 to the z, which is to the x squared natural log of 2 times 2x. So we have 5 to the 2 to the x to the square times natural log of 5 times 2 to the x to the 2 natural log of 2 times 2x. So this is how you can do this with using the chain rule and your exponential derivatives. For our last example, we're going to do one of those kind of examples where we know the outcomes of the derivatives of our functions and things like that, but we don't know what the actual functions are. So we have f of x, so capital F of x, equals f of g of x, and we want to find what is f prime of 2. In this case, we have f of 0 is equal to 3. We have f prime, so the derivative of f of 0 is equal to 9. We have f prime of 2 is equal to 2, and we have g of 2 is equal to 0, and then finally we have g prime of 2 is equal to 3. So now, looking at this, if we wanted to take this derivative, f of x, I'm actually just going to leave it as f of x for now. So let's say we took the derivative of f of x. This is going to be equal to f prime of g of x times g prime of x. So if we're looking for the derivative f prime of 2, this is going to be the derivative of f of g of 2 times the derivative of g of 2. Now, we have the derivative g of 2. So the derivative of the g function at 2 is equal to 3. So I'm going to actually plug this 3 in right here. So this is going to be times 3. And then if we look at this, f prime of g of 2, well, g of 2 is equal to 0. So this is going to be f prime of 0 times 3. Well, f prime of 0, right here, it says is equal to 9. So this is going to be equal to 9 times 3, which is going to be equal to 27. So you'll notice that there was a little bit in here we didn't need, right? We didn't need f of 0. We also did not need f prime of 2, right? These are sort of like red herrings. You had more information and you needed to figure out of these, right? When I took the derivative of this, I took the derivative of f, left the g alone, and then I took the derivative of g. Then, because we were trying to find f prime of 2, this became f prime of g of 2 times g prime of 2. So we needed g prime of 2 and we needed g of 2. So we needed these two. Once I plugged in this g of 2, which was equal to 0, I had f prime of 0, which means I needed f prime of 0. And then with that, I was able to take all the numbers I needed to solve for it, and I was able to get 27. So that's it for our lesson for the chain rule. What we're going to do now is the next lesson, which is still technically part of the chain rule. We're going to be looking at implicit differentiation. I wanted to specifically keep this one as a separate lesson because this is one where I feel like most intro to calculus students really seem to struggle with. So I really wanted to focus on it as its own thing so it's not part of some bigger section like chain rule. So I'll see you all in the next video, and I hope this has been helpful. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.